Hello, and welcome to a shallow dive on statics. If you're thinking of statistics, like collecting data and data spreads and bell curves, you've made a typo. So, if statics is not how likely you are to win the lottery at the age of 34 on a Sunday, or whatever statisticians do, what is it? If you are currently enrolled in a mechanical engineering program, you've probably heard of it before. Maybe that it's a weed-out class. And that is absolutely true, as statics is the foundation of very many other subjects and applications. Statics is one of the three main parts of solid mechanics, the other two being dynamics and mechanics of materials. But now you might be asking, what is solid mechanics? Short answer, it is a subset of continuum mechanics. For a more in-depth look at continuum mechanics and solid mechanics, check out my other video on the topic. Static, as you may know, refers to something not moving. My fridge is static. It does not move. The door on my fridge is very dynamic. Static is also the thing that shocked you when you went down the plastic slide and touched your buddy's finger in the second grade. But for this video, it's the one about not moving. So, statics is the analysis of an object with an applied force that has no movement. The definition of movement for statics not only means that its relative position does not change, meaning they are in equilibrium, but also that there is no deformation. Deformation is taken care of by the Mechanics of Materials course. But to get to that, you must first understand statics. Things like structures, bridges and trusses, as well as shafts are some examples of the application of statics. So, to recap, before we get into some actual stuff, statics is a body with a force applied that is assumed to be in equilibrium, and that does not deform. Got it? Okay, let's move on. Statics deals with both rigid bodies and particles. Rigid bodies are non-deforming, non-moving geometries where the size is important in the calculations. Particles, on the other hand, do not deal with size. A particle can be infinitely small or a bolt the size of your head. On those two, forces are applied. First, we must go over some basic physics to refresh your brain. Newton's laws. Number 1. If net force is 0, the object is either at rest or maintaining a constant speed. Number 2. Force equals mass times acceleration. Number 3. Every action has an equal and opposite reaction. Now, the next topic is scalars versus vectors. A scalar is basically a unit that consists of one quantity of magnitude, such as mass or time. A vector needs more than one, its magnitude and direction. When a force is applied, it can be represented by a vector. The direction of the force application is very important. I cannot stress enough that force application must take direction into account. I was working on a project where we were working with carbon fiber composite tubes. As some of you may know, a composite is a mixture of two materials, with the stiffer material being the fiber, surrounded by the more elastic material known as the matrix. I hear lots of talk about carbon fiber being a magical, super light, strong, and tough material, and they're embellishing, but pretty accurate to have such excitement, because composites are excellent. The orientation of the stiffer fibers in the carbon fiber tube was in the direction along the tube, so it was strongest across the length of the tube. We applied a force in testing that was not in the direction, and we caused delamination and subsequent failure in the tube, which was expected because we understood that the direction of the force was where the carbon fiber was weak. So, the quick lesson is carbon fiber is, quote, super tough and strong if you use it right. Now that you have force is vector smashed into your brain, we can move on. I'm going to assume you've remembered vectors and vector addition from Physics 1 in high school by now, and have figured out that you can use that to add a bunch of forces together to get a resultant force. So, if someone applied 30 newtons of force at 25 degrees and 45 newtons of force at negative 45 degrees, you could vector addition yourself a resultant force. Now that you can simplify forces, what do we do with them? Well, basically, the goal is to be able to find forces at points along whatever the problem is. Primarily, the reaction forces are the end goal, but not always. Reaction forces are that equal and opposite reaction part that makes the total force equal to zero in statics. Well, now it's time to move on to moments. A moment is the rotational force per unit length around a point by a force application. But rotation is movement, and statics doesn't move. Correct. Good. So, we know that in statics, the moment always equals zero. And moment can easily be calculated by understanding perpendicularity, meaning the distance to the point of the force application from the point where the moment is being taken, multiplied by the force, gives you a moment. The summation of all of these gives you the moment around that point. So, let's do a quick example to tie everything together. What we have here is a bar shown as AB pinned to an anchor point at A, and a wire shown as BC that is connected to anchor point C. Two forces of 90 newtons are applied at bar AB at the points specified, so we want to find the reaction forces at point A. Do we have all the information necessary to do that? Let's find out. First, we need to find the angle of ABC. Using basic trig and the dimensions given, we can find that the angle is 45 degrees. Now that we have an angle, we can put a resultant force at B that replaces the reaction forces of C, as shown by the top equation. But we do not know the value for C, and to get that, we can use the moment. As we know, the moment must equal zero, and is the perpendicular distance from A to these forces. So, from point A to point C, not to point B, is 0.2 meters horizontally and 0 meters vertically. So, in the equation, there is C times cosine 45 degrees multiplied by 0. That is not shown, just to make sure you're paying attention. The first 90 Newton force is 0.1 meters horizontally, and oh no, we have no idea how far away it is vertically. We could try to guess by taking out a ruler, making a scale, or we could not worry about it because we only need the horizontal direction as the force is downward, so only the perpendicular distance is necessary. Same with the second 90 Newton force. With one unknown variable, we can easily solve the equation for C, which is the resultant and not C in the y direction. Now, we can solve for the reaction forces at point A knowing the value of point C. Starting in the x direction, first we pick which direction is positive. Of course, I chose to the right as shown by that thing. Summing the forces in the x direction is very simple, as there are only two to worry about, the x component of C and the x component of A. Doing some trig, we know that C is going to the left, so we make it negative as left is not right. Since the summation is 0, the x reaction force at point A is just the opposite sign of C's x reaction force. And finally, the y component is a summation of all the y forces, with up being the positive direction. It's very similar to the x directions equation, just remembering that the c is not positive because the arrow points more up than down, but because of math. Subtracting the 180 newtons from the calculation of c's y component gives us our A reaction force in the y direction. And now you have a shallow idea of what statics is. There's plenty more to talk about statics, or in this case, barely talk about it, but that's for a later installment.